Hello students, in this video we'll see how to compute the moment generating function of a Gaussian random variable. Let's consider a standard normal random variable x whose PDF is 1 over the square root of 2 pi e to the negative x squared over 2. Let's compute the expected value of the exponential of t times x, or the moment generating function. Well, the expected value of e to the tx will be 1 over the square root of 2 pi, the integral from negative infinity to infinity of e to the tx, e to the negative x squared over 2 dx. And now we could write this as 1 over the square root of 2 pi, the integral from negative infinity to infinity of e to the negative 1/2, and then I can have an x squared over here. And since I have a positive tx over here, I'll put a negative 2tx, and then I'll have a dx. And what I'll do is I'll complete the square in this expression. So what we'll do is we will add in half of this squared. So we'll add and subtract half of 2tx, which will be just a t over 2 squared. So we'll just have a t squared. So if we do that, our integral becomes 1 over the square root of 2 pi, the integral from negative infinity to infinity of e to the negative 1/2 x squared minus 2t x plus t squared minus t squared dx. And so now these first terms over here are a perfect square. And so what we have is we have a 1 over the square root of 2 pi, integral from negative infinity to infinity of e to the negative 1/2. And then this will be x minus t quantity squared, and then minus t squared dx. This negative 1/2 times negative t squared is a positive t squared over 2. Does not depend on x, so we can pull that out. So this is e to the t squared over 2 divided by the square root of 2 pi, the integral from negative infinity to infinity of e to the negative 1/2 x minus t quantity squared dx. And now we can make a substitution. We can let u be x minus t. And if we do this, our integral becomes e to the t squared over 2 over the square root of 2 pi. The integral, the limits of integration will not change, negative infinity to infinity of e to the negative 1/2 u squared du. And now we observe that this expression over here is just the integral over the entire line of the PDF of a normal random variable. So this must be 1. So this will be e to the t squared over 2. And then we will have a times 1. And so that says that the moment generating function of x at t is e to the t squared over 2. So as an application of this, note, of course, m of 0 is always equal to 1. But m prime of t is going to be t e to the t squared over 2. And therefore, this tells us that the expected value of x, which is mx of 0, mx prime of 0, is 0. If we do the second derivative, we'll use the product rule. It's the first function, t, times the derivative of the second function, which will be a t e to the t squared over 2, plus the second function times the derivative of the first function, and that gives me a 1. So this tells me that m double prime x of 0 is going to be equal to 1. And that's exactly what we expect, because this tells us what the second moment of this random variable is. And so in general, we can see that if we do this calculation over and over and over again, all of the odd derivatives evaluated at 0 will be 0, and then all the even derivatives will give us some contribution. So a normal random variable only has non-zero even moments. Thank you very much.